this paper. So if you go to channels, all of the technical papers are prefixed with paper hyphen and then the name of the paper. So this is paper hyphen network assisted non-contiguous, so on and so forth. So I think you should be able to find that. So put your questions there. I encourage you to put them, ask questions as the presentation is going on. So when we get to the Q&A session, we have a few queued up, and that way we can make efficient use of that somewhat limited Q&A time. So with that, I will go ahead and see if Kaushik can start his presentation. So our first speaker is Kaushik Suresh, who's from The Ohio State University, who's going to be talking about his paper, Network-Assisted Non-Contiguous Transfers for GPU-Aware MPI Libraries. Oh, and he can hear me now. So Kaushik, if you can hear me, go right ahead. It's all yours.
Thanks, Scott. Thanks for the introduction. I hope you can hear me.
We can hear you. Yep, you're good. And we can now see your screens. So take it away.
Yeah, sure. Hi, everyone. I'm Kaushik Kandadi Suresh. I'm a fourth-year PhD student working in Dr. D.K. Panda's group at The Ohio State University. My current research involves optimizing point-to-point and collective primitives in CUDA-aware MPI libraries. Today, I'm going to be presenting our paper, Network-Assisted Non-Contiguous Transfers for GPU-Aware MPI Libraries. So first, let me begin by introducing the problem statement. So GPUs are gaining prominence in modern HPC clusters due to their compute capability and power efficiency. And in all of these GPU clusters, MPI is widely used for large-scale parallel systems applications. And these MPI applications tend to have non-contiguous data exchanges. So in this slide, we show the use cases of such non-contiguous exchanges in HPC applications. So in the top part, you can see a 2D stencil layout. So in this type of an exchange, typically there is a 2D grid, and you see that the edges shaded in yellow color, and one of these edges may not be contiguous in memory depending on how the data is arranged. So this type of multidimensional stencil pattern occurs in many HPC applications like NAS, MILK, WRF, etc. And in the bottom part of the slide, we see the data layout used in NAS LU application. This is a 3D grid, and again, the points shaded in blue and red colors are the edges that are exchanged across the MPI process. And MPI provides derived data types or DDTs to represent these non-contiguous layouts in memory. So given that these layout exists in HPC applications, several researchers in the past have optimized such non-contiguous exchanges. And the common scheme that has been used for GPU-based non-contiguous exchange is to pack the data to a contiguous buffer and then exchange and then unpack on the receive side. And so many optimizations were towards optimizing the pack and unpack kernel. Another kind of optimization is to overlap the launch of multiple pack kernels with the data exchange itself. Or the third one is to fuse multiple kernels to, amortize the overheads. And in this slide, we quantify the pack overhead incurred for internode GPU-based exchange. We modified DDT bench, which is a benchmark suit for non-contiguous kernels. So we modified it to add GPU support, and we used MILK kernel in that application. And we profiled it for different input parameters. And the y-axis is the total latency. And you see the percentage of pack and unpack cost compared to the total cost. And we see that depending on the input sizes, the cost could go as high as 40%. Given that there is pack cost involved here, none of the past researchers have explored the possibility of avoiding these pack kernels completely and using HCA to do such operations. So in this slide, we show that HCAs can directly gather data from non-contiguous memory regions and transfer the data, and they can scatter the data to the destination memory regions. So this feature is available in modern HCAs, And user mode memory registration is a feature in Mellanox HCAs. This allows us to create something called M key and map them to non-contiguous memory regions. And once that is done, any RDMA operations can be carried out over non-contiguous memory regions. So the advantage that this feature provides us is it makes sure that it gathers the data and scatters the data. Thereby, we don't need to write explicit pack and unpack kernels on GPU or on the CPU side. So in this slide, we quantify the overheads associated with such pack-free scheme like UMR. So UMR requires something called M key creation and also mapping of that M key to non-contiguous buffers. So these two are some expensive operations, and M key creation could cost up to few hundred microseconds. And this graph shows the overhead of mapping M key to the buffers. Again, we have used milk as our example for different input parameters, and we have quantified the percentage of M key mapping cost compared to the total latency. We see again that depending on the layout, it could go as high as 63% of your total exchange time. And after mapping M key, sender and receiver may need to exchange several M keys to actually carry out the transfer. And the number of M keys again depends on the layout that is being used. So this could again have an impact on your total performance time. So given these overheads, the question that we ask is, can we make UMR viable or comparable or even better than pack-based schemes for internode exchanges? So in this paper, we proposed UMR-based design for exchanging non-contiguous data for internode transfers. And then we enhanced them by providing some caching mechanism to amortize the overheads associated with UMR. And finally, we show the usefulness of this scheme at the benchmark level and at the application kernel level by comparing it with other MPI libraries. Let's move on to the design section now. So in this slide, we have outlined the overall protocol that we used and also the DDT processing steps that we have used. So our overall protocol is an RDMA write-based rendezvous protocol. So in this, typically sender sends RTS packet to the receiver, and then receiver sends a clear to send or CTS packet to the sender. And once the sender gets that packet, it can perform RDMA write operations. And after that is done, sender sends FIN packet to signal the completion. So in these kind of protocols, typically RTS and CTS packets are used for exchanging additional metadata like buffer addresses and R keys that facilitates the exchange. And in processing DDT, first the sender and receiver parses the DDT handle to obtain a list of IOVs. So DDT handle is something that is given in the data type field in MPI send or receive or any other primitives. So the MPI library parses that to obtain the list of IOVs. And IOV is a structure that contains the address and length of a contiguous memory block. So any non-contiguous layout can be represented as a list of IOVs. So in pack-based designs, once the sender or receiver obtains this IOV list, a pack kernel first is initiated, which packs the data from these non-contiguous buffers pointed out by these IOVs to a single pack buffer. And then the data is exchanged using the above protocol to a receiver buffer. And in the receiver side, the data is unpacked from the contiguous buffer to the corresponding memory regions pointed out by the IOVs. So now we see how we use UMR to do a pack-free transfer given a non-contiguous layout. So this figure indicates the list of IOVs where each contiguous block has its own address and size. And once that is obtained, we need to register each of them with the HCA. And once this process is done, we map all of these memory regions to M key. So M key this way, we let the HCA know that this particular, any operation on this particular M key corresponds to these contiguous, these non-contiguous memory regions. So similarly, the receiver also has to do a similar operation. And once a process has both an M key pointing to a local non-contiguous memory region and a remote M key which is pointing to a remote non-contiguous memory region, any RDMA write operation can be performed just like a contiguous RDMA write operation. So now the onus of gathering the data from the source, from the layout pointed by the source M key, and scattering the data to the layout pointed by the destination M key is given to the source and the destination HCAs. And here there is no explicit packing or unpacking that is needed. So in this slide, we show how we map the M keys to the memory regions. So for simplicity, we first fix a particular chunk size, and we use a sliding window-based approach to map M keys to these IOVs. First of all, a single M key cannot be mapped to all IOVs because of the hardware limitations. So we first fix a chunk size, and in this case, the first M key and the first chunk size covers the IOV 1 and 2 and some portion of IOV 3. And then the window moves to offset of chunk size, where this covers some portion of IOV 3 and most of the IOV 4. Here we map it to M key 2 and so on until we reach the end where we map the remaining IOVs, in this case, to M key 3. So this way, we have used 3 M keys to map the entire layout. So any operations that needs to be done on, say, these portion of IOVs need to use this M key. Similarly, any non-contiguous operations that has to happen on these two memory regions should be using this M key. So now, after the mapping is done, we need to agree upon a correct, the sender and the receiver need to correctly agree upon a chunk size. So we use a consensus logic to do that, because the senders and the receivers layout may always not be the same. So the logic is as follows. First, sender selects a particular chunk size, and then it sends it to receiver. And then receiver sees if that chunk size fits its memory constraints and hardware constraints. And based on that, it proposes the final chunk size and sends it back to the sender. So in this example, sender first sends a large chunk size which covers both IOV 1 and 2. And receiver finds that this same chunk size covers all 4 IOVs. But the hardware on the receiver side, say if it doesn't allow more than 2 IOVs per M key, so the receiver reduces the chunk size and sends this to the sender. And this also fits the sender, and finally this becomes the agreed chunk size. This way, by agreeing upon the chunk size, sender and receiver make sure that the total number of chunks in the messages is equal to the number of M keys generated, and the total number of RDMA operations that is performed will be equal to this number of M keys. And this slide puts everything together in perspective. So here we see that first both sender and receiver starts by registering their layouts and parsing the DDT. Both sender and receiver does that. Then sender sends its chunk size and its layout information to the receiver. The receiver, after finding the appropriate chunk size, maps its chunk using the sliding window approach to the M keys. So in this case, there are 2 M keys. And the receiver sends in the CTS packet these list of M keys and also the agreed chunk size. And sender performs a similar sliding window-based approach to map its M keys to the chunks, to the IOVs. And once that is done, all the sender needs to do is post, in this case, like 2 RDMA operations, one for this M key and the other for this M key. So here, as we previously discussed, sender is not doing any explicit pack and unpack operation. So when the sender posts the send from this M key to this M key R1, the HCA takes care of the offsets and everything. So all we need to make sure is the size of the layout pointed by these two M keys should be same. And HCA will take care of gathering the data from the source side and scattering the data in the destination side. So in this slide, we talk about the enhancements that we have added on top of this basic proposed UMR scheme. So here first, we look at amortizing the cost of creation of M keys. So we, instead of creating M keys every time in the critical path, we move it to the MPI unit and we maintain a pool of M keys. And an auxiliary thread adds more M keys to that pool whenever it finds that the count of that pool is reduced to 50%. And another important thing is, generally in HPC-based DDT applications, the applications tend to use same layout again and again multiple times. We use this to our advantage to propose M key based caches, and this is one of the advantage that we get with pack-free scheme. Unlike in the pack-based schemes, even though the same layout is used again and again, we still have to pack the data to the buffer and then exchange it every time. So in this slide, we first talk about the structure of the M key, M key cache that's mentioned here. So the main purpose of this cache is to amortize the mapping of the M keys to IOVs and exchange of M keys in the CTS. So we have two types of M key caches. One is the local M key cache, and the purpose of the local M key cache is to avoid the mapping that we explained previously. And the structure of the cache is as follows. So it is basically a hash table indexed by your base address and DDT layout. So this is the DDT layout and the agreed chunk size. And the value is the list of M keys that has been mapped. And we also have something called rank map on the receiver side. This rank map lets the receiver know that to which sender that it has already sent the M keys to. This way, the receiver can decide not to send the set of M keys to a particular sender based on the value in the rank map. And the second type of cache that we have is the remote M key cache. So the main purpose of remote M key cache, actually the remote M key cache resides in the sender side. And this cache is used by the sender when the receiver does not send the remote M keys, because the receiver knows that sender already has cached this layout. So the structure of the cache is as follows. It is a two-level cache. At the top level, it's an array which is indexed by the remote rank. And at the second level, you have a hash table. And again, the structure of the hash table is similar to this, where you have the base address, layout IDs, and the chunk size. And the value is the set of M keys. And cache eviction here will happen whenever the DDT handle is destroyed at the when the layout is basically at the type free time, like when the transfer is done, at that time we free the entries in the cache. In this slide, we show the impact of the UMR caches that we propose compared to the default scheme. We have used modified version of OSU OMB benchmark with MPI type vector DDT support. and the block size that we have used is 1 KB, and the gap between them is 2 KB. And we have tried this for other block sizes as well, and we see like similar performance. And the main observation that we make is increasing block count here degrades the performance of the UMR default scheme. For example, here you see that it's almost 2x, and here it jumps to 3x. And both M-key mapping and exchange contribute to this degradation. And particularly the impact of M-key exchange is more prominent in this case, because the number of IOVs has a direct impact on the number of M-keys that is created. So that is why we see a huge difference in the cache versus the default scheme. So next we move to our performance evaluation. So we have implemented all our designs in the MBAPitch MPI library, MBAPitch GDR MPI library. It's a popular MPI library that has been in the market for over 21 years now. And we have performed our evaluations on 2 different clusters. One is MRI and the other is Theta GPU cluster. And the libraries that we used for comparison were GDR 2.3.6 and OpenMPI 4.1.3 and UCX 1.12.1. These were the latest libraries at the time of our development. And at the benchmark side, we have used OMB with vector DDT support. So, and at the application kernel side, we modified DDT bench to add GPU support, and we have evaluated some of the popular kernels. So in this slide, we look at the vector benchmark result. Here we show that the vector benchmark of block 1 KB and 2 KB for different number of block counts. And here pack GDR and pack staged are 2 other schemes that we compared with our proposed UMR scheme. So in pack GDR, the data is packed to the GPU, and then direct GDR is used to exchange the data. And in pack stage, the data is packed and then is staged to the CPU, and then it is exchanged. So we see that the proposed scheme is able to do better than both pack GDR and pack staged for both 1 KB and 2 KB block length. And we have also tried for even larger block lengths as well. And in particular, the UMR performs up to 2x better than pack GDR and 3x better than pack staged scheme. And now we move on to the application kernel result. The first kernel that we show is the milk application kernel. So here in the x-axis, there are different input parameters that we tried. And y-axis, we show the speed up compared to the performance of OpenMPI. And this kernel uses a nested vector data type, and it uses 4D phase exchanges. And here again, we do see that the proposed scheme is performing like up to 15% better than a GDR, and is at least 10x better than OpenMPI plus UCX. And this we see that the block lengths used in these layouts, when we profiled that, we found that it was from 768 bytes to 6 kilobytes. And next we move on to NAS MG's performance. And in this kernel, it does 3D phase exchanges again with nested vector data types. And these are the 3 inputs that we tried, and the block lengths for these inputs go up to 6 kilobytes. And here again, we see that the proposed scheme, the UMR scheme, is able to perform 50% better than the GDR and 30x better than OpenMPI plus UCX. And the main reason why we see improvement here is for these kinds of layout, it is beneficial for us not to pack, and also the UMR caching here kind of helped us to overcome the overheads of UMR. And now moving on to the final kernel, even in this kernel, similar to the previous results, we see a good amount of improvement. And the layouts used in this kernel was for these input parameter was like 4 KB of block length, and the counts varied from 32 to 128 bytes. Sorry, 32 to 128 blocks. So this brings to the conclusion. So to conclude, we first pointed out that past research work on GPU non-contiguous internode exchanges did not use these hardware-assisted features. So we proposed an UMR-based hardware-assisted scheme, and we also proposed efficient cache-based mechanism to optimize such schemes. And finally, we showed the efficiency of our scheme both at the micro benchmark level and at the application kernel level. And in the future, we'd like to extend this support for other AMD GPUs and also evaluate these designs on large-scale HPC applications. Thank you for patiently listening. I'm open to questions now.
Great, thank you, Kaushik. That was a really interesting presentation. It doesn't look like we have any questions in Slack right now, but if you have questions, I encourage you to put them in Slack. And if we don't have a time, we're right at the boundary here. So it may have to be that, oh, okay, it looks like somebody raised their hand. I don't know if there's a way for you to unmute. You might try putting your question in Slack if you can. I think it's Donglai. You might, I'm not sure there's a way for me to unmute you. So if you could put it in Slack and Kaushik can try to address it there, that would be, I think, the best at this point. I would like to ask just one question before we move on to the next is, so in your experiments, you have sort of, it looked like basically sort of 3 variables. You have block count, block size, and stride. Is that characterizing the memory you're moving accurately?
Yeah. So the input parameters of the application translates at the end of the day, the layout is described by your block length and the gap between the blocks and the number of blocks. Yeah.
So the performance of this this sort of scatter gather approach, do you have a sense of which of those 3 variables the performance is most sensitive to?
Yeah. So it actually depends on both block length and count. So if you increase the count to a very high value, the scatter gather really has so much overhead that it can't perform very good. And again, it performs well for large block length layouts generally.
So is there a point at which the block length gets small enough that it makes more sense to try to write like a hand-packed kernel rather than?
Yeah, exactly.
Okay.
So for after a certain block length, when it's very small and the number of IOVs are large, it makes sense to use a packed kernel. Okay.
Do you have a sense of where that cutoff is?
Yeah, so we have seen that below 1 KB or 512 bytes block length, it's generally efficient to use packed kernel, but that again depends on other factors as well. Like for CPU-based exchanges, it is different, and for GPU-based exchanges, again, it becomes different. Yeah.
Gotcha. Okay. In order to try to keep us on schedule, I think we'll wrap it there. I would encourage anybody who has lingering questions to engage with Kaushik on our Slack channel. And with that, we'll move on to the next one. Thanks again, Kaushik.
Yeah, thanks, Scott.
Okay, so the next paper, let's see, hopefully this time video will work. Okay, so if all went according to plan, everybody can see that screen, and hopefully when I press play, we'll be able to hear it. So our next presentation is a recording from Yao Xin from Pengcheng Laboratory, and it's entitled Updatable Packet Classification on FPGA with bounded worst case performance.
Hello everyone, my name is Yao Xin. I'm a research associate at Panda Laboratory. The paper I present today is titled Updatable Packet Classification on FPGA with Bounded Worst Case Performance. Here is the outline of my presentation. The first part is the background of our work. Nowadays, the network functions virtualization and software-defined networking have emerged as solutions for data centers that can provide flexibility by implementing a software-based network to provide diverse services and applications. Virtualization has enabled tens to hundreds of virtual machines per service in data centers using multi-core CPU technology. However, the network functions of the virtual network protocol stack in data centers are updated frequently and increased all along. As a result, packet processing functions such as classification, routing decisions, encryption, decryption, etc. have grown exponentially. Worse still, the traditional CPUs in servers not optimized for packet processing are not efficient to implement in software. To release the burden of CPUs in servers, semantic based on FPGA has been increasingly adopted to offload these functions. Thanks to its flexible programmability, high performance, and rich capacity. Among these, packet classification is a fundamental and essential task. The purpose of packet classification, which would be referred to as PC here, is to find a matching rule from a classifier for each incoming packet and apply a corresponding action to the packet. Each classifier contains a root table, and each rule can match against the packet headers in a number of ways, including exact match, ranges, and wildcards. Here is the framework of an example classifier. PC has been well studied for almost 20 years, and many algorithms have been proposed. These can be categorized broadly into four major approaches, as shown in this picture. That is, exhaustive search, decomposition, decision tree, and tuple space. Next, we give a little review on decision tree-based PC, which is most relative to our work. The decision tree-based PC can be described from a geometric view. The root node of the tree covers the whole searching space containing all rules. Each rule is considered as a hypercube in searching space. They work by partitioning the searching space into smaller subspaces recursively until a predefined number of rules are contained by each subspace, and the number is named bins. Each incoming packet defines a point in this searching space and would be searched from the root level by level to a leaf node, in which a matching rule would be found. According to the partitioning method on searching space, current decision trees can be categorized broadly into two major approaches: equal-sized cutting and equal-dense splitting. Splitting-based decision trees divide the searching space into unequal-sized subspaces containing nearly equal number of rules. Methods such as hypersplit, parasplit, smart split, etc. belong to this kind. In contrast, cutting-based decision trees separate the searching space into many equal-sized subspaces using local optimizations. According to the bit selecting mechanism, these cuttings can be further categorized into two major approaches. First, to select orderly from the most significant field bits to the least significant field bits, such as high cards and hypercards. Second, to select discretely among arbitrary field bits, such as modular PC, as well as our proposed cake tree. Here is an example of these two techniques. Next is the motivation for this work. In the last 2 decades, FPGA has been increasingly researched as a favorable platform for packet classification. However, there is still no single hardware architecture that can meet the demands for PC in data center scenarios, especially the large-scale rule set supporting and faster dynamic rule update. The dynamic rule update means without pre-computation of memory content. The major current FPGA implementations include two types, which are decision tree-based and decomposition-based methods. The decision tree-based designs have a fast classification speed, and they support large-scale rule set. However, they still face a great difficulty in rule update due to the notorious rule replications. Furthermore, the features of unbalanced and unbounded depths in decision trees result in a high dependence on rule size and the resource waste. As a cutting-edge FPGA-based packet classification technique, the recently proposed bit vector decomposition approach could achieve a good performance in both classification and update. However, the scale for vector is restricted by FPGA resource. Thus, only small-scale rule sets can be applied. So none of them can address the demands well. Most importantly, as far as we know, there is no algorithm designed from scratch for FPGA, so the advantages of FPGA cannot be fully explored in these algorithms. To address this issue, the cake tree was proposed by us, which is dedicated to FPGA recently. And this is a framework of a cake tree, which is a multi-tree scheme. It has several key features to take advantage of FPGAs to the full side. First, trees are dynamically and recursively constructed without rule replications. Second, it has multiple evenly distributed decision trees, which can fully utilize the parallelism of FPGA. Third, tree depths and bins are strictly limited, so each tree would not be too large, which is worst case bounded. This figure shows the process of cake tree construction. For simplicity, it controls the number of levels and the roots of each tree by kicking roots out of current tree during construction in a recursive manner. The recursive process continues until no roots left, which might result in multiple decision trees with evenly distributed depths and leaf node rule number. By minimizing the search delay among different decision trees, this even feature can improve the overall search speed, thereby preventing the so-called bottleneck effect. Next, I will introduce the proposed hardware design for the cake tree. In most decision tree-based designs, fully pipelined architectures are adopted as they can benefit from the high frequency. However, there are still several problems to be resolved. This is an example for pipeline architecture. Each level of tree nodes and rules would occupy a pipeline stage with a RAM, and stages are separated by registers. We can notice that the nodes at all tree levels are unevenly distributed, and the number would be explosive in post-level nodes, which would cause hardware resource unbalance. and the number of pipeline stages cannot be too large. So only a limited number of tree levels would be supported, which is highly dependent on specific root size. And the storage is too scattered alongside the stages, which is difficult for real-time updates or tree reconstruction. To address the above issue, we designed a suitable set of storage structures for decision trees. Nodes in a tree are divided into intermediate nodes and leaf nodes. Each node carries searching information, and each leaf is associated with a root subset. Two turntable-like data structures are designed for nodes and roots, which are called node table and root table. They link back and forth to facilitate root updates. These two types of tables are stored in two centralized on-chip RAMs instead of distributed ones as in a fully pipeline design. Therefore, the tree traversal to search a root is converted to the addressing process. This design has three major advantages. The architecture does not depend on specific root size, and the level of nodes could not be restricted. And it facilitates real-time root updates, and the roots could be traced back to upper-level nodes with cached node information. This is top-level classifier architecture, which is corresponding to the multi-tree scheme of cake tree. Each processing element corresponds to a tree. The real-time root update is a major focus of this work, and to prevent the repeating updates happening in multiple PEs, we adopt a parallel search serial update strategy. As each PE processes root search and update separately, each PE has two sets of interfaces, one for root search and one for update. The search command would be delivered to all PEs for parallel execution as shown with black arrows, whereas the update command is only distributed to the first PE and executed serially in following PEs as shown with blue arrows. In such method, the update is decoupled from search and can prevent the same update happening in multiple PEs. For the search, the result of all PEs are merged and parsed in pairs by the result resolver level by level. The update result, however, goes through each PE in turn with the commands. Instead of fully pipeline design, the architecture of the search tree PE adopts a centralized memory and a serial access method. It consists of a node searcher and a root processor module, each having a RAM to store node table and root tables respectively. The node searcher traverses the tree nodes level by level from the root by reading linked node table entries. When a valid leaf node is found, the root subset address will be delivered to the root processor, which will linearly search the RAM and take the appropriate actions of search, delete, or insert according to the operation code. To enhance memory usage, we implement multiple search units to work in parallel, since they can access the memory in different time slots with limited query time. The advantage of this architecture is that the dynamic update can be well supported. The root processor has two updates paths to rewrite the new contents of different RAMs. As we said previously, the search result of multiple Ps need to be parsed in parallel level by level, and the number of trees can be random and unpredictable for any given set of rules. For the purpose of supporting arbitrary tree numbers, we introduced the idea of modular in the result collection design, which is a multi-level result parser with two input resolver as the basic component. Accordingly, the results of trees are parsed hierarchically in pairs, so the number of inputs need to be a power of 2, which would be supplemented with empty trees. This picture shows the basic resolver. It aims to resolve two issues. The first is the processing of out-of-order results due to the existence of multiple search units and the different processing delays of packet. According to this issue, each input channel has an independent RAM to reorder the results, and the packet ID would act as the writing address. Once a predetermined number of results have been written, the results of both channels are concurrently read in order and compared by priority. Rules with higher priority are output to the FIFO controlled by the bus interface to the next level module. The second issue is the speed of producing results of different trees is not the same, which might result in overflow for one RAM. We designed a data flow balancer accordingly, which dynamically monitors the amount of data flowing into the two channels and controls the bus interface in real time, so that the input speed of the results on both sides is roughly equal. In the next section, we present the performance result after implementation of our design. This is the experimental setup for the evaluations. First, we generate the text rules using the tool of class bench, where 3 types of rule size with 100K size are generated, which are ACL, FW, and IPC respectively, with a total of 12 rule sites. The selection bit length for each node splitting is fixed to 3, and the max tree depth and the bins are set to 8 and 10 respectively. The search unit number of node searcher and rule processor are set to 5 and 6. And finally, the evaluation metrics include classification and update performance and search latency. Because of the distinct characteristics of each rule site, the resulting storage organizations are different. To achieve the optimal performance for a specific rule site, the hardware configurations for various rule sites have been customized and fine-tuned, which are listed in this table. It mainly shows the storage configuration of the first 3 trees, which contain the vast majority of rules. RAM types include distributed, block, and outer. Because our hardware architecture supports real-time rule updates, sufficient spare storage space should be allocated for the search tree in each PE in advance, in case there are more insertions than deletions during updates. This design is implemented on our Xilinx Vertex UltraScale Plus FPGA equipped with extensive Ultra RAMs. Multiple computing cores for classifiers are set by taking advantage of Ultra RAM to achieve high performance. This table summarizes the number of accommodated computing cores, resource usage, and the maximum frequencies after implementations for various rule sets. It's natural to note that the memory, including Ultra RAM and Block RAM, is the most consumed resources. We evaluate the performance of our FPGA implementation in terms of throughput, include packet classification and rule update throughput, measured in units of MPPS and MUPS. MPPS means million packets per second, and MUPS means million updates per second. Performance varies according to different rule types. The classification throughput distributes between 100 and 250 Mbps, with an average value of 183 Mbps. Among them, the performance of the rule sets for ACL2 and FW4 lags far behind other rule sets, mainly due to the bottleneck effect caused by the excessive number of trees they generate. On the other hand, with the exception of the ACL2 rule set, the range of updates throughput does not fluctuate much, with an average of 3 MUPS, which is sufficient for most scenarios. We have also calculated different latency values per packet for benchmark rule sets, including average, worst case, and best case latencies. The latency is closely related to several factors, such as the number of trees, the depth of the tree, and the number of leaf nodes, memory access latency, etc. Although our latency is not very advantageous compared to some pure pipeline designs with only a few stages, it is trade-off to support dynamic rule updates and large-scale rule sets. Nevertheless, we aim to reduce latency in our future work. Here comes the conclusion. We designed and implemented an efficient hardware architecture based on the recently proposed click tree algorithm, consisting of multiple balanced trees for bounded depths, capable of entirely using the FPGA's advantage. Instead of fully pipeline design, we adopt multiple computing cores on the top level. We propose a parallel search and serial update strategy for PEs in each classifier to decouple the search and update process. The parsing of multiple search results adopts a modular and hierarchical design, supporting almost an arbitrary number of trees. Experimental results show that it can achieve an average throughput of 183 Mbps for classification and 3 MUPS for updates for various 100K scale rule sets. Thanks for watching.
Great, thanks, Yao. Can you hear me?
Yes, I can.
Okay, great. It doesn't look like we have any questions right at the moment in Slack. See if there are any stray comments in Zoom. It does not look like it. So I'll go ahead and get us started. So in one of your figures, you showed a plot that had the maximum number of updates and then a characterization of the classification speed. Do you have a sense of how those numbers compare to the current state of the art? It didn't look like it was on that figure.
Okay, because the previous FPGA-based decision tree design didn't support the update. So we have mentioned the performance for classification only in our paper, but here we didn't show because that no one can support update well. So we only show our performance in this presentation.
I see. So I guess one of the questions that somebody using this might want, somebody who's a user of this might want to know is how much classification performance am I sacrificing in order to get that update capability? And I apologize, I don't have the figure in your paper in front of me right now. Do you have sort of a ballpark of what that comparison looks like?
Okay, that performance can satisfy, depends on the language requirement for the real system, because different grid have different requirements. For example, if we have a 100 Gbps requirement, then the throughput would be about more than 200 Mbps. But for 40 Gbps requirement, then the throughput would be about 100. So it depends on a real system. Okay.
The other question, since it doesn't look like we have any questions coming in at least in the experiments you showed in this presentation, you sort of fixed the number of trees and the depth of the trees. Is that accurate?
Yes, we set the parameters fixed because we need a fixed depth to generate a fixed hardware.
Sure. And I guess my question is, how did you settle on those particular values, and what does it look like when you change, if you need to change those values for some reason? How does performance affect it?
Okay, we have tried many times to find the optimal value between the tree numbers and the depths, because the lower the depths, the more tree numbers. So we need to make a trade-off between these two values, and that value we selected is the optimal for our implementation and the performance. So that's maybe a trial and error experiments and the finitude number of values, I think. Okay.
All right, well, it looks like we have come to the end of the session. I think the next thing on the agenda is we have a 15-minute break. And so we'll resume at 2 o'clock. Thank you all for attending, and we'll see you for the panel.
Thank you, Dr. Scott.